Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss classical entropy expression. Let's begin. Entropy. The definition of entropy by using statistical mechanics. The definition of entropy by using statistical mechanics. S is equal to K log W. K S is the entropy, K Boltzmann's constant, W thermodynamic probability. From Maxwell-Boltzmann statistics, the expression for thermodynamic probability. From Maxwell-Boltzmann statistics, the expression for thermodynamic probability is given by thermodynamic probability W is equal to n factorial multipliers, that I from 1 to k gi to the power ni divided by ni factorial. We are almost familiar with these terms, whereas n is the total number of particles, gi is the number of elementary cells, that is divided as we divide the ith compartment or ith interval. Ni is the number of particles in that of ith compartment. This is the expression for thermodynamic probability by using Maxwell-Boltzmann statistics. Let me take logarithm on both sides. Taking logarithm on both sides, we get log W is equal to log n factorial log A into B, that is log A plus log B. Here log A as n factorial, B as the rental term. So log n factorial plus that multiplier change to summation over I from 1 to k. Simply we write summation over I, and expanding log A by B as log A minus log B, again log A to the power m, that is m into log A. The entire formula now used to express that expression I. Here we obtain ni log gi minus log ni factorial. Next, log n factorial. Now expand by using Stelling's approximation, that is log n factorial is equal to n log n minus n plus here summation over I ni log gi minus, again Stelling's approximation we have to use, ni log ni minus ni minus minus plus plus ni is equal to n log n minus n plus summation over I ni log gi minus summation over I ni log ni plus summation over I ni. So n log n minus n plus summation over I ni log gi minus summation over I ni log ni plus, that is the summation over I ni, that is total number of molecules n, plus n minus n cancelled out, the term exists n log n plus summation over I ni log gi minus summation over I ni log ni. Now the value of ni can be put by using Maxwell-Boltzmann statistics. From Maxwell-Boltzmann distribution law, ni is equal to gi into e to the power minus alpha into e to the power minus beta into ui. Ui is the energy of the particles having that of ith compartment. Now the expression of ni is put here. So n log n plus summation over I ni log gi minus summation over I ni. Here in place of ni we substitute gi e to the power minus alpha e to the power minus beta into ui is equal to n log n plus summation over I ni log gi, expanding that logarithmic bracket minus summation over I ni log gi minus summation over I ni log e to the power minus alpha. Next minus summation over I ni log e to the power minus beta into ui. Okay, plus minus, these two terms are cancelled. Next n log n minus summation over I ni log a to the power m, that is m into log n, here minus alpha into log e minus summation over I ni, again that formula minus beta ui into log e. As we know log e is equal to 1, as log e is equal to 1, so the value of log e is put, then n log n minus minus plus alpha as constant to outside summation over I ni log e as 1, here minus minus plus summation over I ni beta as constant to outside ni into uy is equal to n log n plus alpha summation over ni, that is total number of particles, that is n, plus beta, here summation over ni into uy, that is the total amount of energy u. Okay, as we write summation over I ni is equal to n, which is the total number of molecules, and summation over I ni uy, that is u, that is the total amount of energy, as you say in that of Boltzmann statistics, e to the power minus alpha is a constant. Here e to the power alpha is a constant. Let that e to the power minus alpha is equal to a, which implies alpha is equal to minus of log a. Okay, and beta is equal to 1 by kt. Just I write it here, beta is equal to 1 by kt. In that of expression we put n log n alpha value as minus log a into n, and is n log a, n log a plus beta is equal to 1 by kt, here u by kt. From these two terms n as common, that is log n minus log a plus u by kt, is equal to log a minus log b, log a by b, it is n by a plus u by kt, as total number of molecules divided by the constant a is equal to z, which is the partition function. That is n log z plus u by kt. This is the value of log w. Now we can put that value in equation number 1 in order to calculate the entropy. To calculate the entropy of an ideal gas, the entropy of an ideal gas, we have to put the expression of log W in equation number 1. We get S is equal to K. In place of log W we substitute N log Z plus U by KT, or entropy S is equal to NK log Z plus KK cancel out, that is U by T. For an ideal gas, the total energy U is equal to 3 by 2 NKT. So the expression of entropy S is equal to NK log Z plus U as 3 by 2 NKT divided by T. Now TT cancel out. The expression of entropy is equal to NK log Z plus 3 by 2 NK. That is the expression number 4. Equation number 4. Again, what will be the value of that partition function? We can put here to calculate the entropy of an ideal gas. We know the partition function for an ideal gas in continuous energy level. For continuous energy level, the partition function Z is equal to 1 by HQ integration from minus infinity to plus infinity e to the power minus e the total energy, that is a function of xp divided by kt into d tau, whereas d tau is the volume element of phase space. One by SQ, that integration from minus infinity to plus infinity, the expression of energy in terms of momentum as p square divided by 2m. So the expression will be p square divided by 2m kt d tau, that is the volume element of phase space, phase space volume is the position into momentum. Here the position as dqx, momentum dqp as you consider in 3 dimension. Therefore 1 by SQ, that integration from minus infinity to plus infinity e to the power minus p square divided by 2m kt, this one is dqp as dqx integration will be v, which is the volume. So this is v into that integral. Now v divided by s cube, that integral, minus infinity to plus infinity e to the power minus p square by 2m kt into dp whole cube. That is a standard integral. Standard integral as integration over minus infinity to plus infinity e to the power minus alpha t square dt is equal to pi divided by alpha under root is equal to v by h cube, that integral value as in place of alpha, that is 1 divided by 2m kt, so its value will be 2 pi m kt as under root, that is 3 by 2. This is the expression for partition function for an ideal gas, that to be in continuous energy level. Now by putting the value of z in the expression number 4, we can obtain the entropy. So equation number 4 becomes entropy S is equal to Nk log the value of z as v by h cube 2 pi m kt to the power 3 by 2 plus 3 by 2 Nk. Now we can solve it. Nk log a into b, that is log a plus log b 2 pi m kt to the power 3 by 2 plus 3 by 2 Nk. Next Nk, if we take common on these two terms, we obtain here log a by b log a minus log b plus here 3 by 2, then the bracket terms as log 2 pi m kt plus 3 by 2 as Nk common on these two terms. Now Nk log v minus log s cube plus 3 by 2 log 2 plus 3 by 2 log pi plus 3 by 2 log m plus 3 by 2 log k plus 3 by 2 log t plus 3 by 2 within that of bracket. Look that bracket terms. Here log h cube 3 by 2 log 2 3 by 2 log pi 3 by 2 log k, as k is the Boolean constant, and 3 by 2. These are the constants. By combining all these constants, we can simply write one constant. So it will be Nk log v plus 3 by 2 log m plus 3 by 2 log t plus c. one constant, we use instead of that entire constants. So S now written as this, and that S is the expression for entropy, which is called classical entropy expression. This is called classical entropy expression, classical entropy expression. And by using that classical entropy expression, we can easily derive Gibbs paradox and Shakoter equations in upcoming videos, where the constant C is written as minus log SQ plus 3 by 2 log 2 plus 3 by 2 log pi plus 3 by 2 log k plus 3 by 2. From all these constants, we use one single constant C. So with the help of this video lecture, we understand the concept of classical entropy expression. First, the statistical definition of entropy, then Maxwell-Boltzmann statistics. We use the expression for thermodynamic probability. Mathematically we proceed, and finally we obtain thermodynamic probability log W as that one. Then we put the value of log W in expression number 1. Value of log W is put in that of expression. Again, the partition function Z for an ideal gas in continuous energy level, this, that value of Z is put it, and solving it we obtain the classical entropy expression. So with this useful and informative notes, let me wind up the session. Thank you.